Next up, we have Chris Skardon. Chris is a developer with Branch, and he has a real passion for databases. He is the maintainer of the .NET Neo4j library, and in this talk, we're going to be discussing graph databases. What are they? How can they be used? And why should you be using them? Enjoy the session.
Okay, hello everyone. My name is Chris Skardon. I'm a freelance .NET graph database engineer. These are all my details. As this is a video, we're going to be able to come back to it, so we may as well just crack on. Okay, so today we're going to talk about, I'm going to talk about what is a graph database. After that, we're going to go into why you would use a graph database, and after that, we're going to go into the uses of a graph database, and hopefully towards the end of this, we'll come to the conclusion that graphs win, and those of you watching will be wanting to try out a graph database, and hopefully wanting to play around with one and see how everything goes. So I guess let's start off with the basics. What is a graph database? So at a base level, we need to know what a database is, right? Because otherwise, we're jumping in at the deep end. But a database is a structured set of data that's held in a computer. It's available and accessible in a variety of ways. Things like your file system is a classic database. Okay, if you store data, you can access it via the file manager or a command line prompt. But traditionally, when we talk about databases, we talk about relational databases. And these are the sort of databases that we use day in, day out. So SQL Server, MySQL, Postgres, Oracle. And these are the ones which we're taught about on a daily basis at universities or schools. Typically, every project you start is going to have a relational database in the background. LAMP is MySQL. All these things together are the way which our databases are used. Next, we have NoSQL. NoSQL databases were the new kids in town. They're the databases which don't rely on using relational databases. They're not based on structured query language. And these are a variety of different types of databases. So we have Redis, your key value type ones. We've got React, MongoDB, Couchbase, which are both document DBs. Icon-wise, I've gone with a key and a pair for Redis. And after that, we also have graph databases. Now, graph databases technically are NoSQL databases, but for the purposes of this talk, we've separated them out. And there's quite a few on the market for graph databases. There's Neo4j, Cosmos DB, Neptune, OrangoDB. And all of these have various levels of how long they've been around and how performant they are. He wanted to visit Königsberg, and he wanted to go to each part of Königsberg, and he wanted to cross all of the bridges of Königsberg. So these are the bridges. He wanted to cross them, but he only wanted to cross them once. He's a king. He likes to go make his people happy, and he knows that when he crosses the bridges, he makes his people happy. Off you go, Kingy. Okay, so what he's also aware of is that if he crosses a bridge more than once, there's the risk that maybe some Republicans or some of his other people who he's managing, sorry about that, will get cross with him and throw tomatoes or anger of him. And he doesn't want that. He only wants to cross that bridge once, because no one wants an unhappy king. Unhappy kings lead to death and generally bad things in any environment. So what he does, he rings up his friend, his mathematician friend, Leonhard Euler. Obviously, he doesn't actually ring him. This is 1735. He's probably just brought him along with him. And he says to him, "Hey, Lenny, I'd really like it if you could work out if I can actually visit every section of Königsberg, cross each bridge only once." And Lenny goes, "Hey, Kingy, I think I can." At that point, the king does stop him. Say, a little bit informal here. I'm not pleased if you calling me Kingy. It's the king to you. Leonard probably is. I'm sorry. Okay. Yes, I can do this. Can I have your map? At this point, King goes, okay, you can have my map. This is an expensive map. You know, we've been doing this for a long time. I'm sure you're aware of how much maps cost in this day and age to get hold of. Please be careful with it. So the king gives the map to Leonard, who probably scrawls all over it. The king, in an unhappy situation now, has decided to leave and let Leonard get to it before he gets even crosser. So Leonard has highlighted the maps as we did before. He's drawn in the river in a bit more of a clearer way, and he's scribbled out a bit of green. He gets a bit further, he's a bit bored, so he colours it in fully, and changes the colour of the bridges for some reason. We start to see a few things here. So he's got these different shapes. He's got this big green blob at the top, the green blob at the bottom, the one on the right, and the one in the middle. And he sort of looks at them and thinks, well, okay, maybe I don't really care about the size of these. All I really care about is that they exist. And the same with the bridges. I only care they exist. So you can extract them into circles and relationships. So his next stage is to take it to this level. The numbers inside each one of these blobs represents the number of bridges that connect to it. And using this, he manages to work out the fact that the king can't visit every bridge in Königsberg around, or every land spot in Königsberg around, to cross the bridge at least twice. So there's a much better explanation of the 7 bridges of Königsberg online, and it's linked at the end of this, and I wholeheartedly think you should go and look at it and see what she's written. Anywho, so we know a graph database is a database which holds data which is accessible. We know we've got our 3 broad churches: relational, NoSQL, and graph. So let's add our graph database to it. So we use graph structures for semantic queries with nodes, relationships and properties to represent and store data. In a slightly more simple, I want to explain this in a elevator type approach. The graph database designed to treat relationships between the data as equally important to the data itself. And that's hugely important. That's the biggest thing that you need to take from this. The relationships in a graph database are as important as the objects in the database. So in relational database terms, that's saying the join tables are as important as the actual data you have in there. Okay, so why would you go with a graph? Okay, so we know what a graph database is now, but why would you even bother going with one in the first place? Well, graphs show how data is connected. Here we have a graph of the Game of Thrones, and all those lines, they're connections. Right? They're connections between different things. Whether a house is sworn to another house in this case, or whether someone is allied with someone else. The connections aren't just, this is a classic sort of social bit, right? So connections are everywhere. We've got people, place, and events. So, I'm doing this talk for FutureSync. So I now have a relationship with FutureSync. Companies and markets, they all have a link as well. So Software Cornwall sponsors FutureSync. We also have countries, politics, history. FutureSync was based in Plymouth. It still is based in Plymouth, I guess, but now it's online and global. It's also useful in the sciences, arts, and teaching. I don't have a picture for that, but anyone who's ever looked at a graph of the atom structure of water, for example, will have seen 2 H's and 1 O, and they're always joined together by their bonds. Technology, networking, machines, applications, users. I'm recording this on my laptop, which is connected to my Wi-Fi, which is then connected to YouTube or wherever this gets uploaded to, and each of those is then, you're then looking at that as well. and then that is linked to your machine. Software and code dependencies. If you're writing a JSON, something to parse JSON in C# that you wouldn't bother, you'd pull in the dependency from somewhere else. That dependency then has a graph on other dependencies. Git is a classic example of a graph that is used by thousands, millions of software developers every day. And that's a graph. You have your check-in is followed by another check-in, which then has maybe a branch going off it, which is then merged back into it. It's all a graph. And there are connections between criminals, fraudsters, and their behaviors. And these are classic ones, right? These are things where criminals are doing bad things, and we're using connections to try and figure out how they do that. So, has a criminal connected to another criminal? What was a criminal connected to a bank which was robbed? Okay, so that's where our connections are. And there are good reasons for using a graph. Okay, the first one is probably the most important one, is that your data is connected, and that's important to you. If you have a load of data and it's all connected, but you don't care about those connections, then you don't need a graph database, right? You just need the data. But if you care about the fact that Chris bought this product, or that Tony sold that product, then that's where graphs can become immensely useful. You can see who bought what, when they bought it, and then you can start to say, well, not only did he buy it, but he's friends with this person who's also looking at buying the same stuff, so maybe he can influence him. Simple modeling. So the really nice thing about the graph is it's easier to model. Anyone who's ever done a SQL database or relational database diagram like this one, so this entity relationship, knows that a lot of the tables we add into them are tables that exist purely for the modeling. So link tables between where someone works, which departments they work in. We have to have a link table that says person A works in departments B, C, and D. When you try and explain these sort of diagrams to domain experts, the people who work in it, so the people who manage HR, they don't understand it. When you try and explain it to C-level, so your CEOs and stuff, they go, I don't know what that is. C-level here represented by cats. When you take a graph database, it's much simpler. Even the domain experts themselves can draw it and they can look in. It's easy to see that a tweet here, for example, mentions a user. You can read that very easily, and you can access it very easily. Okay. Excuse me. So they're also schemaless. Not all of them. The main ones we talk about here, so Neo4j is the primary one I'll be talking about, is schemaless. So you can store whatever you want into it. If you need to change your data, or you want to change what you're storing in it, you can do that. Your nodes, which are the blobs, you don't have to worry about what they store or whether they all have the same thing or different things. You can add stuff in on the fly. You don't have to write a script to update your database. And the main key one as well is performance, which is got by index-free adjacency. So now I've dropped the term index-free adjacency in. Let's have a quick look at that. So index-free adjacency, what is it? Right. Firstly, it only applies to native graphs. I appreciate I've now added in another term. It's important, particularly when you're looking at getting a graph database for your own work, that you understand that not all graphs were created equally. There are two broad types. There's native graphs and there's mixed graphs. So native graphs were always built to be a graph database. They had the benefits of index-free adjacency because they're built from the ground up to use it. Mixed mode databases, so that's Cosmos, Neptune, Orango, they're built on top of another database model. For example, Cosmos is built on top of a document database. And generally, with all of these, you end up using an API which is translating a graph query into a document query. As a consequence, you effectively have a middle layer between the two, which can cause you some performance issues. So, very nice native databases. Let's have a quick look at an index-free adjacency example to try and make it a bit more clearer. So, I'm based in Cornwall, which is good. So the scenario. I've made some pasties. They look good pasties. And Tony really wants a pasty. Obviously, he wants a pasty. So the index-free route, I walk out my door, I point in Tony's direction, and I deliver the pasty to Tony. Tony gets a hot pasty, everything's good. In the index cost world, and I'm using cost purely as an antonym to free, I walk out my door. Okay, so far, so the same. I go to the central index, I wait in my line, and I have to wait there because there will be other things in line waiting to get access to that index. I get to the front of the line and I search my index, and at that point I'm basically saying, hey, can I have Tony's address? At which point the index goes, yep, let me look that up for you, gets it, and gives me the coordinates for Tony. I then deliver my pasty to Tony. Obviously the downside to this is that Tony now has a cold pasty. And there are some people who say that cold pasties are as good as hot pasties. They're wrong. I think we all should agree that hot pasties are the best pasties. So that's a sort of rough walkthrough of how the indexing works, but on a slightly more technical nature. If this is your relational database, where you have a table for employees, a table for departments, and then a lookup table for department members. So basically what we're modeling here is which departments Alice in this case is a member of. When we do this, we start at Alice, so we get 815, so we do one index lookup to find Alice. Then we go to department members and we have to do another index lookup to find which department she's a member of. So we then have 3 results, which we then have to go to our departments table and do another 3 index lookups. Okay, so we have a dynamic query time. If Alice is joined to another department, there'll be another index, so that will increase the cost for us. We have an O n log n performance issue here. Okay, we're using a binary search, we're just splitting it. It's pretty quick, but obviously the more we have, the slower it will be. We look at the graph version of this. We have a node called Alice, and Alice belongs to these labels. All we have is the first index lookup where we look up Alice. Subsequently, all we're doing is pointer chasing. So we have a constant query time of O log n for this. Okay, so this is one of the key benefits of a graph database, right? The ability to basically skip very quickly into the nodes we need to find. Okay, there are also bad reasons for using a graph database. Yeah, with everything that's good, there's always a bad. And the biggest one on this is the fear of missing out. Okay, so this trend just up to the end of 2019 shows the different databases, and it shows the graph database, graph going all the way up. You shouldn't use a graph database just because it's super popular, right? That's not what you should do. The fact that it is so popular probably means some underlying facts that it's helping a lot of companies work through use cases, which we'll talk about in a minute. But don't use it just because it's popular. Okay. So uses. Firstly, it's not just for social things. Okay, it's not just for modeling Twitter or your Facebooks, and it's not just for bridge traversals either. There are lots of other uses which you can use a graph for. So, got financial crimes, where we're looking to see if people are committing fraud. It's easy to see when you have someone who is maybe you're a company which offers £20 to every person who you bring into the company. and you find there's one person who's brought in 100 people, but none of those 100 people have brought in anyone. So it's a very distinct pattern. You can look for those people. You can find them very easily. Drug discovery, there are companies out there doing drug discovery with graph databases. Recommendation engines are a very classic approach. I bought something, I'm friends with you, maybe that's, other people have also bought the same thing, and we're all friends with you, maybe you should buy that thing. Customer segmentation, easy to group people into different types of things, even by where they've bought, what they've done, where they live. Cybersecurity, pretty much tied into the financial crimes territory. Churn, imagine I've got a company where I have 1,000 customers, hopefully it's a big company that, and one of those customers is friends with 500 of them and he leaves. Is he going to take all of his friends with him? Predictive maintenance. I know Alice is rebuilding one of the machines, which means that some of the other machines aren't working. So maybe we can then look to also fix all of those machines at the same time, or run a load of other updates on them. And then the last fallback is your search and MDM, which is our master data management, where maybe we have a customer database of users, and we also have an HR database for the people, and we also have a support database for the people, and we want to have one master view on that person, but we want to link all the other databases together. In real life, Walmart use this for real-time recommendations. I mean, all of these companies are using Neo4j for doing these. We've got fraud detection, IT operations, knowledge graph from NASA, searching from ICIJ, IAM from Microsoft. And ICIJ is one of the ones that's most interesting. You might know them from the Panama Papers. The ICIJ took 11 million documents, roughly 2.6 terabytes of data, and working with engineers at Neo and another company called Linkurious, they stored all of this data into Neo4j and provided some user interfaces to look at it. And if you've ever looked at any of the pages about the Panama Papers on The Guardian, New York Times, you'll have seen something similar to this. And this is all powered from the database, which is run by Neo and the user interface by Linkurious. And it allowed non-techie journalists the ability to actually be able to go through and look at all of these dodgy companies, or not dodgy companies, and be able to see very easily where things were linked and how things were linked. It's a very clear way to be able to read information, which is, if you were to do this in a SQL database, a relational database, very hard to make visible, and the queries to write it are also incredibly complicated. So very briefly on how we use a property data model. So we have things called nodes. Nodes are what we've talked about so far. They're the blobs, the circles, and they represent objects in the graph. And we can categorize them using labels. So I have 4 nodes here. I've got a person node, I've got a conference node, and I've got a company node. Labels group things and make it easier to actually work out what things are. We also have relationships with a graph database. Relationships have a type and a direction. Okay, direction makes sense. A conference liking a person is unlikely. Conferences don't actually do that, where someone does like a conference. And then we have properties, and we apply properties to people, nodes or relationships, and that's important. So we can have single properties, or we can have multiple properties. We can have them on our relationships. The information we have here is very simple. You can look at this and you can give it to anyone and say, okay, well, who is Chris friends with? Oh, he's friends with Tony. What conferences does Chris like? He likes FutureSync. Okay, and FutureSync is in Plymouth. Great. Okay, it's very easy to read these things. It's very simple to query them. So the graph databases solve everything. I mean, obviously the answer to that is no. You should always use your right tool for the job. If you've got very discrete data, documents, things like that, then use the other NoSQL database. Use a document database for it. they're very good at that. That's what they're for. If you have sort of mid-range stuff, no big connections, but you're not too worried about it, then go with relational DBS. They're also very good for things like tabular data. But if you have highly connected data, which you're genuinely really interested in, then go with a graph database. They are easier to maintain for your connected data, they're high performance, and you generally use very little resources. Compared to a relational database, they are tiny. What I'd also argue, and this is the last bit, so well done, is that we should poly-database all the things. In modern development now, if you go around most software houses, you'll see people writing code in maybe Java, maybe C#, maybe Python, JavaScript, and people are doing that for there's particular reasons those languages are good for doing it, right? Python, if I'm writing natural language processing, I'm going to use Python. It has the toolkits and the ability to do it. If I'm doing something in like file management, I probably use C# because that's what I know. But there's nothing that says I can't do those two things and join them all together. When we come to databases, we tend to have one database, and that's our database for the whole system. What I'd like to see more is that you have your documents in a document database, you have some tabular data in a relational database, and then you use a graph database to connect those two together so that you're querying the graph to find your data and you're pulling the data from other places. We're very much stuck in this one database world, whereas we should move into a multi-database world. So lastly, resources. I would strongly recommend you go to Neo4j and get to the desktop version of it to play around with. It's free and it lets you experiment with how Neo4j works. The All Things Graph, look at that YouTube. She explains the Bridges of Königsberg problem far, far better than I do, and she is very good at it, and lots of other graph problems. And there's me at the bottom. And I guess last thing, remember, it's graphs, not charts. Okay, cool. Thank you.